Hi, I'm Caeden, and here's an explanation on Euler's method. Let's first take a look at a simple example, say the function y is equal to x squared, and we only consider part of the graph whereby x is more than 0. Tangent line approximation is usually used, and it is done by drawing a tangent line at a point of the graph and using its gradient to approximate the value. However, you can see that as x increases, the distance from the tangent to the graph also increases, due to it being non-linear, and this makes it inaccurate. Instead, we can use Euler's method. Euler's method is a technique used to approximate solutions to the initial value problem with given initial conditions. It uses course correction, meaning that the gradient will constantly update, taking small tangent steps, which is known as step sizes h. However, since this is only a method used to approximate, there will be an approximation error to the actual solution, which will be covered later on in the video. Euler's method has a formula yn plus 1 is equal to yn plus h times f bracket xn comma yn. But how do you actually obtain this formula? Let's take a look at this graph over here. The derived function is a gradient of the graph, and gradient can be found using rise over run. In mathematical terms, it is yn plus 1 minus yn over xn plus 1 minus xn. Since we know the gradient is the derived function, and xn plus 1 minus xn is the step size h, we simply plug this into the equation, cross multiply, and we will obtain Euler's method as shown over here. I will now use Excel to show the process of solving the given question. The blue column here represents the number of step sizes needed to obtain x is equal to 1. Let's start off with a step size of 0.1, so the blue column over here will require 11 values from 0 to 10 in order to get x is equal to 1. This orange column represents my xn, and I use the formula b10 plus $b8. b10 is my previous value of xn, which is 0 originally, and b8 is my step size, which is constant, hence the use of the $sign. I can then pull this down, and then I will obtain x is equal to 1. The green column uses this formula, b11 squared plus 1 slash c11, and this represents my derived function when x is equal to n and y is equal to n. As you can see over here, the formula uses the values of xn and yn on the same row in order to calculate the answer for that formula. Lastly, the yellow column represents my approximated answer using Euler's method, which is equal to c10 plus bracket $b8 times d10. c10 is my previous yn value, d10 is my previous derived formula value, and b8 is that same constant step size of 0.1. Now, I can drag both the green and yellow columns down, and we can see that we'll get the final answer of 1.911 when using a step size of 0.1. Now, I will repeat the same process, but instead, I'll use a step size of 0.05. Because it is half of the previous step size that we used, we're going to need to repeat this 20 times instead in order to get x is equal to 1. Using the same formulas as shown over here, we obtain a value of 1.913 when using step sizes of 0.05. Now, let's compare these answers to the answer I obtained using the general solution. The steps to solving an initial value problem using the general solution is to first separate the y and x terms on separate sides, in this case by cross-multiplying. We can then integrate both sides and obtain this equation, which is our general solution. However, we need to find out what c is specifically, so we use the initial values of y is equal to 1 and x is equal to 0. And after finding out c is equal to half, we get this equation over here, which is our particular solution. Lastly, we substitute x is equal to 1 back into this equation and obtain a final answer of 1.915. The negative value is rejected for this question since in the question, it is stated that y must be more than 0. Notice how the final answer varies slightly compared to the answers we obtained using Euler's method. This photo shows the graph on Desmos. The blue graph represents the actual graph, while the green represents the Euler's method when the step size is 0.1, and the purple graph represents Euler's method when the step size is 0.05. For clarity, I drew the graph out over here, but it's not drawn to scale, and you can actually notice that the step size affects the approximation error to the solution. Hence, I can conclude that the smaller the step size, the more accurate Euler's method is to approximating to the actual solution. That's it for my sharing. Thank you for listening.